All right, let's go through the solutions for the problems posted for you guys. So we're looking at continuity on these first few, well, for all of these, just being able to justify that a function is actually continuous at a given point. So let's look at the first problem. All we want to do is be able to sketch some type of situation. So all of ours are going to look very different, but there's some key information that needs to occur here. So if we have our xy plane, f has to have a limit at x equals 3, but not continuous at x equals 3. So I have to think about what that might look like. So I'm going to go ahead and mark this as 3. I'm going to put a hole right there because it's not continuous there, and then I'm going to keep on going. So my limit exists. It's whatever this value is right here at f of 3. But notice that the function is not continuous at 3. So it wouldn't meet the criteria of the limit as x approaches 3 of f of x equaling to f of 3. So since that does not equal, then this function is not continuous. And again, your picture may look different or your graph may look different, but as long as it had that criteria in there, you're good. F is not continuous at x equals 3, but its value at x equals 3 is changed from f of 3 equal to 1 to f of 3 equal to 0. Then f becomes continuous at x equals 3. So we have a graph. We have, again, we're looking at 3 for my x value, and it says that it's not continuous. So I'm going to draw the same thing to f of 3 equals 0. So I need to draw something similar. Let's go back one. So I'm going to put a hole right here, and I'm going to draw a function. It's going to keep on going, and says is it changed from f of 3 equal to 1. So I'm going to put a point right there, to f of 3 equals 0, which is why I have that filled in hole, then it would become continuous. So if we plugged in that hole, then I would have a continuous function. So again, this function as it stands right now is not continuous, but it could be continuous if that one little change was made. For the last one, f has a removable discontinuity at x equals c, for which f of c is undefined. So that simply means if it's a removable discontinuity, it means that it needs to be a hole. So let's just say I have a c value right here. But since f of c is not defined, there's no point on there that I could put in. So in the previous example, we had filled in at f of 3 equal to 1. But in this case, there is no point at this value, but it has to be removable. Remember, your non-removable discontinuities are ones where you have that jump discontinuity. So like here and then there, that would be a non-removable discontinuity. And then also if it were asymptotic, that's also a non-removable discontinuity. For the last one, f has a removable discontinuity x equals c, for which f of c is defined. So again, this is very similar to question number 2. We have a hole somewhere at some c value, and then we're plugging that hole in or we have a plug for that hole somewhere, but we're not actually plugging that hole in to make the function continuous. All right, on this next part, we're going to start entering into some algebra to make things make sense. So first, let's All right, so we need to use the definition of continuity. So I'm just going to go ahead and write that off on the side. That means that my limit as x approaches some c value of f of x needs to exist. So that's condition 1. Condition 2 is that, or I think that's my condition 2, but f of x needs to be defined. So there needs to be a value for that. And finally, f of x as x approaches c of f of x must equal whatever f of c is. And this is really the big one here, right? So we need these two to occur, but these two are going to occur in a variety of different situations. It's not until this happens that we really have continuity. So let's take a look at this first one and see if we can find that value of a. So we're given that f of x equals this function. Obviously, our a is going to be at 1 because we see that if I were to sub 1 in here, I have some type of discontinuity going on. Oh, so we're, sorry. So we're proving that this function is in fact discontinuous. So let's take a look. We're going to start with the limit as x approaches 1 of x squared subtract 5x plus 4 all over x subtract 1. So this limit needs to exist. So we're going to check and see if we can sub that in. So we have the limit as x approaches 1. Let's see if I can factor here. I have an x subtract 4 and an x subtract 1, so I can. And then I can sub that in, so I find out that my limit here equals -3. Now let's figure out what f of 1 is. Well, if I were to look on my graph, I see that I can't put 1 into this function because it's undefined at 1. So f of 1 is undefined. I can't do this fancy little cancel out thing, right? Because it's not, I can't physically put 1 into that function because of this denominator. The only reason I'm allowed to do it here is because I'm looking at the limit. I'm not actually subbing in 1. And 1 is the reason this function's discontinuous. We have a hole at 1. So the reason why this limit doesn't exist is because f of 1 is undefined. And if I were to graph this function, it would look really similar to the graph of x minus 4. So it would have a y-intercept down here at -4. It would be a linear function, but then at 1, -3, so right about here, it would have a hole. So this function would look like this. So notice the limit exists, but this function isn't defined. All right. For our next one, we're going to look at this guy. So we're starting off with somewhat of a piecewise function. We're told that at g of 3, we get 1. So we know g of 3 is defined. So g of 3 equals 1, so my function's defined. Now let's go ahead and check out the limit as x approaches 3. We're going to use the area where x doesn't equal 3 to be able to analyze that. And so I'm going to put this in here. I see that that's easily factorable, so I'm going to go ahead and keep cruising. Now I can cancel those out and sub in. So I get 3 over 3 plus 3, which gives me 3 over 6, which equals 1/2. So my limit exists, so that's a check. So my first criteria and second criteria are met, and now I need to see if these two equal each other. So our problem arises here because the limit as x approaches 3 of g of x does not equal g of 3. Or in other words, 1/2 does not equal 1. And if we were to graph this function, we would have a rational function with a hole at 3, and then we would have a filled in hole at 3 with an output of 1. And so you could graph this in Desmos quite easily. I'm going to keep cruising just for time. All right, for the last one, we're given another piecewise function, but in this instance, it's going from either direction. So we have from the left and we have from the right. So anytime I have a situation like this, I am going to start off by finding h of 0. And you want to be careful that you're looking in the right spot. So h of 0 is where this is greater than or equal to, because there's that equal to piece. So I'm going to start off by checking to see if it's defined. I get, so I'm going to get h of 0 is just going to be 0. Now I'm going to see if this limit exists. So I need to look at the limit as x approaches 0 from the left, which is this function, e to the x. For this limit to exist, it must equal the limit from the right, which is x squared. So e to the 0 power, anything to the 0 power is 1. 0 squared is 0. Those two do not equal each other. The limit does not exist. and that is why this function is not a continuous function. All right. For our last one, this is where the algebra, I was mistaken, this is where our algebra is coming into play. So what we're going to be doing with these ones, and these are some of my favorite problems, you're trying to find values of k and m that make the functions continuous everywhere. So we're going to use our criteria of continuity to be able to find these unknown values. And what we're going to do here is use a lot of systems of equations to help us out, a topic that you covered very, very well in both Algebra 1 and Algebra 2. And pre-calculus, actually. So let's take a look at what this is going to look like. Cover this guy. Oh, I don't want that. Let's cover this up. Have a little bit more working space. All right. All right, so we need to know for a function to be continuous, remember the limit has to exist, and then the function needs to be defined, and then additionally they need to equal each other, both the limit and the function. So I'm going to start by just saying, we see that we're coming from two different avenues. We're coming when x is less than or equal to 2, and we're coming when x is greater than 2. So this piece right here tells me that the limit from the left is actually going to be equal to whatever f of 2 is. So I don't need to specify that. The real question here is this limit going to exist? Because we're coming from two different directions around this point too. So I'm going to go ahead and spell that out. We have the limit as x approaches 2 from the left, which is kx squared. That needs to equal the limit as x approaches 2 from the right of 2x plus k. And you need to write this step out. When you're checking for continuity, you can't just draw a picture and say, oh, it looks like they connect, we're good. You really need to do it out algebraically, mathematically. So now I can just go ahead and sub in here. I'm subbing in for x, not k, so keep that in mind because it says x approaches 2, so I get 4k equals, I'm going to sub in here 4 plus k, and now I'm just going to solve for k. I'm going to subtract on either side. I get 3k equals 4, I divide, and I get k equals 4/3. This means for this function to be continuous and my limit to exist, k would have to equal 4/3. And again, the reason why I didn't have to do f of 2 is because f of 2 is exactly equal to this expression right here in this instance. So you could write that if you wanted to, just to kind of make sure you're covering all your bases, but we would get 4/3 for this problem. All right, for our last problem, again, we're starting, notice now we have 2 points of discontinuity. We're looking both at 2 and at -1. So we have a couple of different ways that we need to attack this. But again, notice that this function is true when for g of 2, it's going to be the same as the limit. And for this function, g of -1 is going to be the same as this limit. So I'm going to start by seeing where my limit exists. So we're going to have the limit as x approaches 2 from the right. That's this guy because x value is greater than 2. So that's x squared plus 5. That needs to be equal to the limit as x approaches 2 from the left of m x plus 3 plus k. So I'm going to go ahead and sub in again. I don't have any k values or m values in here, so I just get 4 plus 5 equals, when I sub in over here, I get m multiplied by 5 plus k. So I'm left with 9 equals 5m plus k. Next up, I'm going to look at the limit as x approaches -1. These are all the values that are greater than -1, so I'm coming from the right for this first expression, and that's going to be that m times x plus 3 plus k. Oh, -1, I left that out. Oh no, I didn't. Okay, we're good. That's a little divide there. Okay, and that needs to be equal to the limit as x approaches -1 from the left of 2x cubed plus x plus 7. I'm going to sub in 1 here. I get 4m plus k equals, and when I substitute in, oh, -1, my apologies. That's going to be a 2m. So -1 plus 3 is 2, 2m. plus k. Negative 1 over here, that's going to give me a negative 2 subtract 1 subtract 7, plus 7. So I have 7 minus 1 is 6, subtract another 2 is 4. And now I'm going to take both of these expressions and I'm going to do a systems of equations. So I'm going to say, well, I know that 5m plus k equals 9 and 2m plus k equals 4. And then I'm going to subtract through all of these expressions. So I end up with 3m equals 5. So m equals 5/3. And then I can take this and sub it into either one of these. I'm just going to sub in here just because it's easy. I have 2 multiplied by 5/3 plus k equals 4. So 10/3 plus k equals 4. I'm going to subtract 10/3 over to the side. 10/3 is the same as 3 1/3. So I have 4 subtract 3 1/3, which is 2/3. Or you could look at this as 12/3 subtract 10/3. But you get k equal to 2/3 and m equal to 5/3.